Right, sir. So let us consider three layers, AA dash, BB dash, CC dash, right? The molecular density. Molecular density is nothing but the number of gas molecules per unit volume. In AA dash, it is n minus lambda dn by dy. In BB dash, n. In CC dash, n plus lambda dn by dy, where lambda is the distance between two adjacent layers. Dn by dy is called as concentration gradient. Concentration gradient. Okay, the number of molecules, the change in number of molecules per unit distance. As we move from bottom layer to the upper layer, if you move the unit distance, how much change in n value? That is nothing but dn by dy. This is known as concentration gradient. So therefore, here we are taking the concentration gradient in three layers. In AA dash, n minus lambda dn by dy. In the layer BB dash, n. In the layer CC dash, n plus lambda dn by dy. So what is lambda there? Lambda is mean prepath. What is meant by mean prepath? This is the average of individual prepaths of a gas molecule. Right, sir? So this is the description of the diagram, right? According to the Joule assumption, as we discussed in the previous class, that the average number of molecules can move in any direction is given by NC bar by 6. If you see the figure, it is very clear that, so the concentration gradient is more in CC dash, right? Compared to the CC dash in the BB dash layer is less. Compared to the BB dash in the layer AA dash is decreased. Right, sir? Here, when we consider a gas in the container, we are assuming that that is the composing of many layers, different layers, right? At some region, the concentration gradient may be more. At some other region, the concentration gradient may be less. That means at some region, the number of gas molecules per unit volume will be more. At some other region, the gas molecules per unit value will be less. So at the different regions, concentration gradient will be different in the different regions inside the container. Therefore, then what happens is gas molecule can transfer from high concentration region to the low concentration region. So from the high concentration layer to low concentration layer, the gas molecule can transfer. Here the gas molecule is transferring from one region to another region. Gas molecule is having some mass. So here the mass transport is taking place. Right, sir? So because of the mass transport, because of the transportation of the mass from one region to another region, the diffusion phenomena takes place. So the diffusion is nothing but, the diffusion of gas is nothing but, here the gas molecule is transferring, the gas molecule is moving from high concentration region to the low concentration region. So that process continues until the steady state attains. So throughout the volume of the vessel, at every point, the concentration gradient remains constant. So for that time interval, this process goes on. Right, sir? So here, let us apply the Joule assumption. Joule assumption. The number of molecules transferring from upper layer CC dash to the bottom layer, that is BB AA dash through BB dash per unit area per unit time, J1 equal to n plus lambda dn by d by C bar by 6. We know the formula NC bar by 6. The average number of molecules can move either x direction or y direction or z direction or in any direction, NC bar by 6. Here the molecules are transferring from CC dash to BB dash. So what is the concentration gradient in CC dash? N plus lambda dn by dy. So therefore, instead of n, we are writing n plus lambda dn by dy into C bar by 6. So J1 represents what? The number of gas molecule will transfer from CC dash to the bottom layer, right? To the bottom layer J1 equal to n plus lambda dn by C bar by 6. Similarly, the number of gas molecule transferring from bottom layer AA dash to the upper layer CC dash through middle layer BB dash through unit area, unit time is given by J2 equal to, again applying the formula NC bar by 6. But here, the concentration gradient in the bottom layer, how much? N minus lambda dn by dy. Therefore, instead of n, we are writing n minus lambda dn by dy C bar by 6. This is equation 2. Got my point, sir? J1 equal to n plus lambda dn by dy C bar by 6. J2 equal to n minus lambda dn by dy C bar 6. Followed, sir?
Yes, sir.
Followed, right. So therefore, net the net number of molecules can transfer from CC dash to AA dash through BB dash per unit area per unit time. Here, some molecules are transferring from CC dash to the bottom layer AA dash. Some molecules are transferring from AA dash to CC dash. Therefore, the resultant number, the net number of molecule can be transferred from upper layer, that is CC dash, to the bottom layer AA dash is given by J1 minus J2. J1 minus J2. So that is, we are writing J dash is equal to J1 minus J2. Clear, sir? Okay.
Yes, sir.
J1 minus J2. J1, J2 value by substituting that, n plus lambda dn by dy C bar by 6 minus n minus lambda dn by dy C bar by 6, right? So therefore, J dash is equal to, here the first term n C bar by 6. In the here also the first term minus n C bar by 6 gets cancelled. Then the second term in the first, what is that? C bar by 6 lambda dn by dy minus into minus plus here. Here also lambda dn by dy C bar by 6. We get 1/3 lambda dn by dy C bar. 1/3 lambda C bar dn by dy. Say this is equation 3. But actually, for the diffusion process, the number of molecules can be transferred from high concentration region to the low concentration region. High concentration layer to the low concentration layer depends on 3 factors. One is area of the gas layer. Second, time duration, how much time we are considering. The third one, concentration gradient. So therefore, actually J directly proportional to A, directly proportional to time interval, directly proportional to dn by dy. So by adding these 3, we can write it as J proportional to A T dn by dy. Then J is equal constant D A T dn by dy. So by writing J by AT equal to capital D dn by dy. So J by AT is nothing but the number of molecules, the number of gas molecule transferring per unit area per unit time. The number of gas molecule transferring through unit area in the unit time. Already equation 3 represents the same meaning. So equation 3 obtained by using the kinetic theory of gases. There we use the Joule assumption concept. The postulates of kinetic theory of gases we considered, right? So here generally we are writing J by AT equal to D dn by dy. This is equation 4. Equation 3, whatever represents, the equation 4 also representing the same meaning. Therefore, we can equate the equation 3 and 4. Got my point, sir? Clear?
Yes, sir.
Equation 3 and equation 4, by equating that, J by AT equal D dn by dy, we are equating capital D dn by dy, capital D dn by dy equal to 1/3 lambda C bar dn by dy. Okay, so then dn by dy gets cancelled. Capital D equal 1/3 lambda C bar. So this is the required expression for coefficient of diffusion. So the coefficient of diffusion of the gas capital D is equal to 1/3 lambda C bar. You should know the each symbol in the expression. So what is lambda there? Lambda is main free path. What is C bar there? C bar is average speed of the gas molecule. We know C bar equal formula what? Under root 8 KT by pi small m. Right, sir? So D equal to 1/3 lambda C bar. But according to the Maxwell, what is the mean prepath? According to the Maxwell, the mean prepath lambda equal to, what is the lambda? Lambda equal to 1 by root 2 pi sigma square n. So by substituting that, you will get the expression in terms of n. So that is one thing. So multiplying the equation 5 with the density term rho in the numerator and denominator. So here 1/3 lambda C bar rho by rho, right, sir? But 1/3 lambda C bar rho. 1/3 lambda C bar rho represents what? This is the coefficient of viscosity, right? Coefficient of viscosity in terms of density, we have 1/3 lambda C bar rho. So what we are doing is equation 5, we are multiplying with the density rho in the numerator and denominator. But 1/3 lambda C bar rho is viscosity coefficient. Then we get capital D equal eta by rho. Capital D equal to eta by rho. So from this, we can conclude that the ratio of coefficient of viscosity to density of the gas represents the coefficient of diffusion. So this is one point I want to tell you. And one more is D equal to 1/3 lambda C bar, already we got it. But the mean prepath lambda directly proportional to T by P. So D is equal to what we got, sir? 1 by 3 lambda C bar, where lambda is mean prepath. Lambda mean prepath, it is directly proportional to temperature and inversely proportional to pressure. By substituting here, but here C bar, the average C bar is directly proportional to root T. Okay, so then we can write D directly proportional to lambda, but lambda proportional to T, C bar proportional to root T. By combining this T and root T, T power 3 by 2 by the pressure term P. Have you followed? So what I am saying is D is equal to 1/3 lambda C bar none. 1/3 lambda C bar. But lambda directly proportional to temperature. C bar directly proportional to root T. Therefore, D directly proportional to T power 3 by 2 and inversely proportional to pressure. Okay. So this is important bit in entrance point of view. The coefficient of diffusion of the gas is directly proportional to T power 3 by 2. I told you that in the case of coefficient of viscosity and coefficient of thermal conductivity, there eta proportional to root T and thermal conductivity coefficient K directly proportional to root T. But here the diffusion coefficient directly proportional to T power 3 by 2. Yes, sir. So what I am telling is, what is the diffusion of the gas, how it takes place? When we take the gas in the container or vessel, at the different regions, concentration gradient will be different. Then the gas molecule can transfer from high concentration region to the low concentration region. Hence, the diffusion phenomena takes place. So this is called transport phenomena about the diffusion. So there we are approaching, we are considering the 3 layers, AA dash, BB dash, and CC dash, right? AA dash, BB dash, CC dash, and their concentration gradients, T minus lambda dt by dy, T plus lambda dt by dy, right? So from that, we are taking the number of gas molecule can transfer from CC dash to AA dash through unit area, unit time J1, we have written. Similarly, the number of gas molecule can transfer from AA dash to CC dash through BB dash per unit area, per unit time J2, we have written. The net number of gas molecule can transfer from CC dash to AA dash, J equal to J dash equal J1 minus J2. We got something. But according to general concept, J proportional to E and time duration and concentration gradient, by equating those two expressions, so finally we got capital D equal to 1/3 lambda C bar. 1/3 lambda C bar. So then if you discuss what are temperature and pressure parameters depending on the diffusion coefficient, the coefficient of diffusion directly proportional to T power 3 by 2 and inversely proportional to